In Genshin Impact, one day in Teyvat lasts 24 minutes, though it would be weird for that to be canonically accurate. However, it's obviously not possible for one person to experience 24 hours and only 24 minutes for another, right? Well, physics says otherwise. Hello, Count Sake here, back with another Genshin Impact video. Today, I'm going to be answering the following question. Is it possible for one day on Teyvat to be 24 hours, while also being 24 minutes for someone else, and why? Now, obviously, this isn't really going to be anything lore accurate, as I'm pretty sure Earth doesn't exist within the universe Genshin takes place in. This is just for fun, so keep that in mind. I do think it would be interesting to cover the case where a child was in the abyss for 3 months, but when he comes back to Teyvat, only 3 days had passed. However, that would have to wait for another video, so be sure to subscribe so that you don't miss out on that in addition to the other math and physics topics I put out. Remember to like and share the video with others, and you can also support me with super thanks or by becoming a channel member. Lastly, I would like to thank everyone who participated in the video topic poll, and to Rasbell for making this comment inspiring the topic for the video in the first place. You guys made this video possible. So how is it possible for two people to experience different rates of time? The answer to that question lies in Einstein's General Relativity. Yes, E=mc² guy. But before we can tackle the physics of Einstein's General Relativity, we need to talk about Galilean Relativity. Relativity is about doing physics in multiple reference frames. A reference frame is basically a fancy word for point of view or perspective. Consider this example. When standing still, we can see these ducks are spinning around the knuckle-duckle. However, if we run around the knuckle-duckle in the same directions the ducks are spinning, it suddenly appears that the ducks are just floating right beside the player, barely moving at all. In fact, it actually looks as if the surroundings are spinning, but in the opposite direction of the ducks. So essentially we have two different perspectives, one where there's a person standing still and one where there's a person moving. The question we have to ask ourselves is this: who has the right frame of reference? If you said the person moving, you're wrong. And if you said the person standing still, congratulations, you're also wrong. Neither perspective is correct or wrong. The reality of the situation is that even though things look very different between the still and moving frame, there's something that is consistent between the two, and that is the laws of physics. To be more technical, the laws of physics remain the same for all inertial reference frames. Inertial just means that no acceleration takes place. Let's say we're holding a race between Chevros and Diona with Coach Yan-san watching from the side. A medium female model has a speed of 1.14 meters per second, and the short female model has 0.991 meters per second. I measured these values in the two videos on screen, how to measure distances in Genshin Impact and more accurate speed measurements. From Yan-san's point of view, the environment stands still while Chevros has a speed of 1.14 meters per second, and Diona has a speed of 0.991 meters per second. Based on this, Yan-san can conclude that Chevros is 0.149 meters per second faster than Diona. Now let's imagine if we were in the perspective of Diona. Instead, what would happen is that Yan-san and the environment appears to be moving at 0.99 meters per second backwards, while Chevros has a speed of 0.149 meters per second forwards. Lastly, let's look at things from Chevros' point of view. Similarly, all of her surroundings, including Yan-san, appears to be moving 1.14 meters backwards. As for Diona, she's clearly jogging forwards, but her velocity appears to be 0.149 meters per second backwards. Hopefully this example illustrates how objects move with respect to another and Galilean relativity. Now, I will not cover accelerating reference frames, as that gets complicated really quickly, so I'll leave it at that. The main thing to understand in Galilean relativity is that velocities simply add or subtract. This works really well, but little did we know that this simplicity wasn't the case, and that it's actually more complicated than we thought. When you learn about special relativity for the first time, you'll be taught its two postulates. First is that the laws of physics in all inertial reference frames must be the same. And second is that the speed of light in a vacuum is constant regardless of what reference frame you're in. The first one comes from Galilean relativity. However, the second one doesn't make sense because intuition would tell us that the velocities should just add or subtract. So if an object is moving at 10 meters per second, we expect that from the perspective of that object, light would appear to move 10 meters per second slower. Well, in reality, we just kinda assume that it would be true because it makes the most sense. There are a lot of videos explaining why the speed of light in a vacuum is constant. However, I find that the popular ones are unsatisfying. Oftentimes, they use physical observations of time dilation and length contraction to explain why the speed of light is constant. It's not wrong, but I personally wanted to know how Einstein even thought to consider a constant speed of light in the first place. After all, time dilation and length contraction were phenomena only proven after special relativity was popularized. Now, saying the speed of light in a vacuum constantly is quite tiresome, so from here on out, when I say speed of light, I'm referring to the speed of light in a vacuum. To understand Einstein's motivations, we need to look at Maxwell's equations of electromagnetism. These are a set of equations that explain the behavior of the electric and magnetic fields. I won't solve these in this video as the solution isn't extremely important to this topic, but if you're interested, I have these members-only videos. Anyway, when you solve Maxwell's equations, you get two classical wave equations, one for the electric field and one for the magnetic field. Something about the classical wave equation is that the speed of the wave can be directly calculated with the term in front of the second partial time derivative, which would be the mu naught epsilon naught. When Maxwell calculated the speed of the wave, he found that it matched the speed of light. This is how we know that light is an electromagnetic wave. What's interesting though is that mu naught and epsilon naught are fundamental constants of the universe and don't change. But if mu naught and epsilon naught are constants, then that means that the speed of light is also constant. Maxwell's equations could be wrong and need modifications, or they could be correct. After all, the equations do describe electromagnetism quite accurately. Einstein chose to believe the latter. According to Maxwell's equations, the speed of light is constant, and because this is included among the laws of physics, it follows that in order for the laws of physics to be the same in all reference frames, the speed of light must be constant. This is the reason why Einstein invoked that second postulate. Turns out, this very accurately predicts a lot of phenomena, and a lot of technology, such as GPS, have to account for the effects of special relativity. With the two postulates of special relativity established, let's now talk about one of those effects: time dilation. Imagine we have two people, A and B. Person A is standing still on the ground, while person B is flying in a rocket at constant speed. From the point of view of A, the rocket moves with a speed of vb/a. To understand this notation, this is basically saying the velocity of B with respect to A. So the subscript b/a is B with respect to A. I will be using this notation quite a lot in this video, so do get familiar with it. Inside the rocket, a beam of light bounces back and forth between the walls, which are a distance of w apart. From person B's perspective, the light beam simply moves up and down in place, and measures that it takes Tb with respect to B amount of time for the light to bounce up and down once. From person A's point of view, the light beam moves with the rocket so it travels diagonally. Person A measures that it takes Tb with respect to A amount of time for the light to bounce up and down. Remember that the second postulate of special relativity requires that the speed of light is always constant regardless of the reference frame. Therefore, the speed of light from A and B's perspectives should be the same. Let's start with person B's point of view. Speed is distance divided by time, and we know that the distance the light travels is 2w because the light goes up then back down. Meanwhile, the time is Tb with respect to B. Overall, this gives an equation that the speed of light is equal to 2w divided by Tb with respect to B. Let's shift over to person A's perspective. As we mentioned earlier, the light travels diagonally. Let's define this diagonal distance as capital L. So the total distance that the light travels in Tb with respect to A amount of seconds, or just any unit of time, is 2L. Likewise, this gives the speed of light is equal to 2L divided by Tb with respect to A. If you look closely at the path the light travels, it actually makes a right triangle. So therefore we can use Pythagorean theorem. L squared is equal to d squared plus h squared. The height h is just equal to the width of the rocket w. But what about the horizontal distance d? Well, if you think about it, the whole reason why A sees the light moving diagonally is because the light is inside the rocket, which, from A's point of view, is traveling at a speed of vb with respect to A. Recall that distance is speed times time. The speed is just vb with respect to A. As for the time, since we're only considering half the total distance, it should be Tb with respect to A divided by 2. All that's left now is to combine everything together with a bit of algebra. The first thing we can do is substitute for d and h, which gives this. Next, we can recall our equations from earlier with the speed of light, and then solve for L and W. From here, the equation now is only dependent on the speed of light, Tb with respect to A, Vb with respect to A, and Tb with respect to B. With some clever manipulation and algebra, we end up with this final equation. Tb with respect to A is equal to gamma times Tb with respect to B, where gamma is equal to 1 over the square root of 1 minus Vb with respect to A squared divided by C squared. In this equation, Tb with respect to B is the duration of an event that person B measures from within his or her own reference frame, i.e. the B reference frame. Tb with respect to A is the duration of that same event that was in person B's reference frame, but instead it is specifically measured by person A. Lastly, gamma is known as the Lorentz factor. Let's take a look at this equation and make some observations. First of all, it's important to know that only objects without mass are capable of traveling at the speed of light. This should make sense because everyone sees light traveling at the same speed. If you want an intuitive explanation for why that's true, you can check out this video from Floathead Physics. Anyway, the rocket has mass, so Vb with respect to A must be less than the speed of light. This implies that the Lorentz factor must always be greater than or equal to 1. This also implies that Tb with respect to A must be greater than or equal to Tb with respect to B. Therefore, it's possible for the same exact event to have different durations in different reference frames. From the perspective of A, the event appears to last longer than when we consider B's point of view. This is very non-intuitive, as we expect the duration of events to be the same regardless of your point of view. However, this equation tells us otherwise. Time dilation is a thing. Now, the reason why time dilation isn't very noticeable for us is because the speeds we move at are much slower than the speed of light. To put things into perspective, the fastest man-made object is called the Parker Solar Probe, and it had a speed of 692,000 kilometers per hour, or about 430,000 miles per hour. Let's see how much 1 second for the probe would dilate if we stood still and saw this object pass by. After plugging everything into the equation and calculating all the values, we find that 1 second for an object moving with that speed would be 1.000000206 seconds for us observers standing still. As you can see, the duration increased by only 0.206 microseconds. And this is the fastest man-made object to date. Just to mention, time dilation isn't the only consequence of a constant speed of light. There is also something called length contraction, which basically says moving objects shrink along the direction they're moving from the perspective of other reference frames. In addition, relative velocities are now more complicated. I won't touch upon these in detail as they're not very relevant to this video. We're only considering time dilation today, so yeah. A word of warning. This chapter is the most important to grasp out of all the others. However, the problem is that this is also the most difficult to understand. I'll do my best to explain this concept, but don't feel down if you don't get it or need to rewatch it multiple times. Person B does not feel that time has slowed down. In fact, B feels that time is perfectly normal. The strange part is that person A will also feel that time is flowing perfectly normal. Both still measure 1 second as 1 second. The effects of time dilation can only be seen when someone observes another reference frame moving with respect to their own. For example, when person A observes person B as an outsider to the rocket. Inside the rocket that person B is in, person A will observe that time flows slower for person B. The time that elapses within an object or entity's own reference frame is called the proper time, and it's often notated as tau. In the equation for time dilation, I use Tb with respect to B to represent B's proper time. You have to be a bit careful, as Tb with respect to A is also technically a proper time, but only from A's point of view. It's important to recognize that Tb with respect to A is not B's proper time, but Tb with respect to B is. I will keep using the old notation for now, as I think it'll help with clarity, but I'll end up using both throughout the rest of this video, so yeah. To understand this concept, let's consider an example. Yaemiko and A each have their own clock with a stopwatch. Whatever time is on that person's clock is their proper time. Both of them synchronize their clocks and start them simultaneously. At the instant they start their clocks, A leaves and Miko observes her moving around at 60% the speed of light. This results in a Lorentz factor of 1.25. Miko takes a look at her clock and reads that 1 second has passed. This 1 second is Miko's proper time. However, when she reads A's clock, it doesn't read 1 second. She reads 0.8 seconds. The 0.8 seconds is A's proper time. This should make sense so far because A is moving from Miko's point of view, so A would appear to have dilated time. Now let's go to A's perspective. This is going to be a very big brain twister, so pay close attention. From A's point of view, Miko and the rest of Teyvat are moving at 60% the speed of light, but in the opposite direction. So if A looks at her watch at 0.8 seconds, she does not see Miko's clock at 1 second. Instead, she'll read 0.64 seconds. Funnily enough, if A waits until her clock says 1 second and she checks Miko's clock, it'll say 0.8 seconds. Let me try my best to explain why this isn't a contradiction. To do this, I'll make use of something called a spacetime diagram. For some reason, the standard is to draw the time axis as the vertical while the spatial axis is the horizontal. I don't know why this is the case, but you have to get used to it. In addition, we actually consider the time axis to be the speed of light times time. This is so that the path of a light beam is a straight line at a 45-degree angle. Let's start from Miko's point of view. Miko sees herself standing still, and A is the one who's flying around at 60% the speed of light. Miko's path through spacetime is this red line. For A, her path is this purple line. And lastly, the yellow lines are the paths of light. The grid lines correspond to the current reference frame, so any distance along the vertical is a measure of proper time. It's also worth noting that each grid square corresponds to a distance of 0.5. Since we're in Miko's reference frame at the moment, 2 units vertically corresponds to 1 second for Miko. To her, anything that occurs at the same time appears to be a horizontal line, which is shown as the horizontal red line. But are A's lines of constant time the same as Miko's? Well, it's actually good to be a little skeptical about this idea because we already know that time is relative. As it turns out, A's lines of constant time would be the faded purple line in the background. So, no, they do not share the same lines of constant time. This essentially means that A and Miko will not see things happening at the same time. Things that are considered simultaneous in one frame may not necessarily be simultaneous in another. So at 1 second for Miko, she will look over at A's clock. This might look like 1 second, but you have to remember, we're in Miko's perspective, and we're measuring time with Miko's proper time, which we know is different from A's proper time. To know what Miko will read, we need to see things from A's perspective. Now here's the spacetime diagram, but from A's reference frame. A will perceive herself as the one who is still, and Miko is the one moving away at 60% the speed of light now. Notice that the red horizontal line that was 1 second for Miko is now a diagonal line, so the point at 1.25 seconds is actually the same point that would be 1 second for Miko. The 1.25 seconds is the proper time for A for when she would see Miko's clock at 1 second. Right now, because we're in A's point of view, things that happen simultaneously for A would be along this purple horizontal line. If at 0.8 seconds for A, she looks at Miko's clock, she would read 0.64 seconds as we mentioned earlier. Right now it looks like 0.8 seconds, but again, that's A's proper time. To know what is on the clock, we actually need to go to Miko's reference frame. Keeping our eyes on the purple line and where it intersects the red line, we see that in Miko's point of view, it would be 0.64 seconds, which is exactly as we expect. The paradox arises because we believe that there's some universal clock that everyone obeys and agrees upon, but that's not true. Because time is relative, what might be simultaneous in one reference frame may not be in another. This is one of the early concepts that is taught in special relativity, the idea of simultaneity. People can only really agree that things are simultaneous when they are within the same reference frame. There can be times where events appear to be simultaneous in multiple reference frames, but those tend to be like coincidences. Something to take note about this example is that I used the analogy of reading clocks to showcase the concept of proper time. However, seeing things is a consequence of light entering our eyes, and light has a finite speed. So in reality, a physical clock would actually be more delayed because it would take time for light to travel from Miko to A and vice versa. Don't take the whole thing of reading a clock literally. The concept was to show that people experience time at different rates depending on their motion, and that simultaneous events are also relative. If you're still confused about this, I can recommend Minute Physics video on the twin paradox. There's a chance I could cover this topic myself if I talk about the case where a child experiences 3 months in the abyss while only 3 days passes for Teyvat, so you can go ahead and check it out if you want to get a primer. Also, subscribe so you don't miss out on that video. Before we continue, a lot of the math going forward uses something called Einstein Notation, so it's best to be familiar with it. Throughout modern physics, we tend to use mathematical objects called tensors, and for simplicity, you can think of it as a fancy collection of numbers that has very specific properties. Just like in a hotel, you need to specify the floor and room number to find your room. The same goes for tensors. They have components, but to retrieve them, we need to specify it through indices. I highly recommend this video by The Science Asylum, What the Heck is a Tensor, if you want an intuitive explanation of tensors. Let's start simple. Here are vectors v superscript n and v subscript n. The n is the index, and when we specify a value for it, we can retrieve a component of the vector. However, notice that there are two different notations for the indices. There's a very important difference between putting the index upstairs versus downstairs, as v superscript n does not equal v subscript n. But that distinction isn't necessary for this video. Also, the superscript n isn't an exponent. Exponents in tensors are shown with brackets around it, and then we put the exponent as shown. For a quick rundown of Einstein notation, if you see repeated indices with one in the superscript and one in the subscript, that index is summed over all its possible values. To get the idea, I'll show 4 examples. Try to figure out which indices are being summed over and which ones aren't. So pause the video and try it out yourself. In the first example, there's an I in the superscript of v and in the subscript of x hat, so we sum over I. Here's the second example. There's a q in the superscript and subscript, so q is summed over. While j can be found on the left and right sides of the equals sign, it isn't summed over because it's not found within the same term twice. In the third one, index A is in the subscript of the first delta and the superscript of t, so it is summed over. For index B, it's in the superscript of the second delta and the subscript of t, so B is also summed over. Again, n and m aren't summed over as they aren't repeated twice on the same term. For the last example, there are 3 terms, so we need to go through each one individually. The first term doesn't have any repeating indices, so nothing is summed over. In the second term, the index j is repeated on the subscript of a, and the superscript of x, so j is summed over only for this term. In the third term, the indices k and p are repeated and summed over. Both are in the subscript of b and their superscripts of c and d. Hopefully the notation is a lot clearer now. When it comes to proper time, I personally find that just following the time dilation equation alone can be very confusing. While writing this script, I've accidentally gotten the proper times mixed up, so I had to rewrite sections. Luckily though, there's another way to calculate proper time, and that is done by using something called the Spacetime Interval. This quantity is one of the few things that all observers will be able to agree upon. The spacetime interval is analogous to like the length of a path through spacetime, but it doesn't just account for spatial distances, it also accounts for time distances. If you're wondering how time can be a distance, it's multiplied with the speed of light, which has units of length over time, so time multiplied to length over time is just length. We can calculate the spacetime interval with the following. ds squared is equal to g mu nu times dx mu times dx nu. As you can see, we're already making use of Einstein notation. The indices mu and nu are both summed over from 0 to 3 because we're dealing with 1 dimension of time and 3 spatial dimensions. By convention, 0 is taken as time and 1, 2, and 3 are taken as the spatial dimensions. ds is the spacetime interval. Both mu and nu are indices, g mu nu is the metric tensor, and dx is a displacement vector in spacetime, also known as the displacement 4 vector. The metric tensor is basically a factor that ensures the dot product between vectors remains the same regardless of what coordinates you use, which is particularly useful to us because space and time are relative. Anyway, if you take the square root of this and integrate the expression, you'll end up with a value for the spacetime interval. If we want to calculate proper time with the spacetime interval, we have to realize that objects relative to themselves do not move in space. This implies that the spacetime interval is simply equal to ds squared is equal to c squared times d tau squared, which is equal to g mu nu times dx mu times dx nu. Let's consider the example from earlier. In Miko's perspective, we'll consider A's path from 0 to 1 second of Miko's proper time. We can simplify things since we're only considering time and one spatial dimension. This gives a metric tensor and displacement vector as shown on screen. From here, we can derive a simpler expression for the spacetime interval. What we get is ds squared is equal to c squared times dt squared minus dx squared. Now all we need to do is use a bit of algebra, then integrate. This results in a spacetime interval of 239,833,966.4 meters. Because spacetime intervals are consistent across reference frames, we can use this to determine the proper time that A would have experienced along that path. From earlier, we know that ds squared is equal to c squared times d tau squared, which we can take the square root of both sides, then integrate both sides, which gives s is equal to c times tau. We already know the value of the spacetime interval, and we know the value for the speed of light, and this results in the proper time for A, which is equal to 0.8 seconds. This is exactly what I showed earlier. 1 second in Miko's proper time would end up being 0.8 seconds in A's proper time. So far, we've only considered time dilation due to relative motion. However, there's actually another way for time dilation to occur. To understand where it comes from, we need to take the leap from special relativity to general relativity. In my last major video, What Was Alhaitham Reading?, I gave a bit of a primer for general relativity. This time, we'll be diving just a bit deeper. To review, general relativity is the current prevailing theory of gravity. It states that gravity is not a force, but is actually the curvature of four-dimensional spacetime. The relationship between curvature and energy is shown through the Einstein Field Equations shown on screen. The left side embodies curvature, while the right is the energy. So, where does time dilation come into play? For a quick answer, because gravity is the curvature of spacetime, time itself could be curved, leading to time dilation. For the longer answer, and if we want to get more specific, we'll need to solve the Einstein Field Equations, which means calculating the metric tensor. This is deceptively simple because it looks like you only need simple algebra to solve it, but in reality, capital G mu nu, which is known as the Einstein tensor, is equal to this. R mu nu is called the Ricci tensor, and R is the Ricci scalar. The Ricci scalar is just equal to this. Meanwhile, the Ricci tensor can be expanded further to this. The gamma terms are called the Christoffel symbols, which have this equation. Keep in mind that the indices mu and nu can take on any integer value from 0 to 3, so you actually have 16 different equations. But due to symmetries, the 16 equations actually reduces to 10. All in all, the Einstein Field Equations are a set of 10 second-order partial differential equations, so yeah, trying to solve for G mu nu is definitely not as simple as it seems. Anyway, let's consider the most simple solution to the Einstein Field Equations, the Schwarzschild metric. The assumptions are the following. 1. We have a spherically symmetrical mass without an electric charge that doesn't spin or spins very slowly. Second, T mu nu, or the stress energy momentum tensor, is equal to 0. Three, the cosmological constant, lambda, is equal to 0. Fourth, in the limit as the radial distance approaches infinity, the metric tensor is equal to the Minkowski metric. And fifth, the partial time derivative of the metric tensor will be equal to 0. Due to the spherical symmetry, it would be easier to solve if we used spherical coordinates. Basically, you can imagine that instead of specifying 3 distances, x, y, and z, you indicate how far you are from the origin, which is the radial distance, and 2 angles, which are the latitude and longitude. Anyway, with these assumptions, the metric tensor takes this form. A of r and b of r are functions that need to be solved, which depend on the radial distance. I have an idea for how to solve this, but we'd literally be here for probably another half hour at least, and to be honest, others can do a better job at explaining the process, so I'll stop here and jump straight to the answer. If you'd like to see the full solution, I highly recommend this video by Eigen Chris, Relativity 108a Schwarzschild metric derivation. This is the solution for the metric tensor. Rs is known as the Schwarzschild radius, and it is the smallest radius an object of mass m must be compacted into in order for it to turn into a black hole. An alternative way to write the Schwarzschild solution to the Einstein Field Equations is to write out its spacetime metric, which is also known as the Schwarzschild metric. Hey, remember that we can calculate proper time with the spacetime metric? The general case would be very difficult to integrate, so let's make some assumptions. Consider an object orbiting a planet in a circle with constant angular velocity, omega. Because it's moving in a circle, this means it'll be at a constant distance from the center, so dr is equal to 0. In addition, the circular path around the object allows us to reorient our axes so that the object simply orbits along the theta direction, which means d phi equals 0. Obviously, time will always change, so the first term remains. From rotational kinematics, omega is equal to the first derivative with respect to time of theta. This implies that d theta is equal to omega times dt. From uniform circular motion, the magnitude of the tangential velocity is v theta, which is equal to omega times r. After going through all that algebra, we get this equation. T is equal to gamma prime times tau, where gamma prime is equal to 1 over the square root of 1 minus rs over r minus v theta squared over c squared. The square root term looks like the Lorentz factor, but this time it has an additional term. The rs over r specifically comes from taking into account gravity. This shows that it's possible for an object to be standing completely still in space, and time dilation would still take place because of gravity. If you really want an even deeper explanation as to why gravity causes time dilation, well, the reason is because while you're standing still in space, you actually need to accelerate outwards from the source of gravity in order to not get pulled in. So technically you do have motion, but that motion is only through time. Something worth mentioning is that the Schwarzschild radius is actually quite small. It is only when objects have a lot of mass, like black holes and neutron stars, that Rs over r will actually have any significant impact on time dilation. So now we know the two causes of time dilation: relative motion and gravity. Let's finally answer the main question I posed at the start of this video. Before we continue, I just want to make this clear. What I'm doing in this video is just physics for fun. The numbers aren't meant to be used for lore implications, so if there are any lore enthusiasts around, don't take any of the numbers I calculate seriously. Though, feel free to use the equations I presented if you want to figure out something. Anyway, if you closely listened to my question at the beginning, it was intentionally vague. Let me rephrase. Is it possible for 24 minutes to elapse on Earth, but a whole 24 hours passes on Teyvat? Why don't you take this time to write your answer down in the comments below? Some of you are just gonna continue watching and edit your comment, aren't you? Don't make Cloran come after you. Ah, whatever, just do it for fun. Anyway, the 24 minutes is our proper time because when we play the game, a day on Teyvat lasts 24 minutes. 24 hours on Teyvat simply refers to the proper time of someone on Teyvat. For our calculations, I'll go back to the explicit notation showing who's taking the time. I'll let the subscript T be Teyvat and E be Earth. Since I'm pretty sure Teyvat doesn't have as much mass as a neutron star or black hole, we can say that Rs over r is approximately 0. This means that we can just use the equation we derived using special relativity and solve for the velocity. If we plug in the values for time of Teyvat with respect to Teyvat and the time of Teyvat with respect to Earth, we get... An imaginary number? Okay, something is definitely wrong here. If we look back at our situation, relative to someone on Earth, Teyvat will be flying at near the speed of light. This means someone on Earth would see that Teyvat's time is dilated and would appear to flow slower. Basically, when someone on Earth compares their proper time to that of someone on Teyvat, they will always see that Teyvat's proper time is less than Earth's. Let's remember our example with Miko and A. When Miko uses her proper time to determine A's proper time, Miko will always find that A's proper time is less than hers. It also goes the other way around, as we covered. If A uses her proper time to calculate Miko's proper time, she too will always find that Miko's proper time is less than hers. You can also see this effect using space-time diagrams. Notice that at 1 second of proper time for Miko, she sees that A's proper time is 0.8 seconds, but at the same time, A, at 0.8 seconds of her proper time, will see Miko's proper time at 0.64. So Miko, when she looks at A, sees A from the past, and when A looks at Miko, A sees Miko from the past as well. For any observer who looks at others in relative motion or in strong gravitational fields, that observer will always see all other reference frames have dilated time. So, it's impossible for 24 minutes of proper time on Earth to be 24 hours of proper time on Teyvat. There you go, question answered, so we're good, right? Well, we only considered half the story of someone on Earth. What about Teyvat? Is it possible for 24 hours to elapse on Teyvat, but only 24 minutes passes on Earth? This sounds like the same exact question, but it actually isn't. In this case, someone from Teyvat goes through one whole day while they see Earth moving at a very fast speed. Plugging in the values, here we see that in order for 24 hours on Teyvat to be 24 minutes on Earth, the Earth would have to be moving at 99.986% the speed of light relative to Teyvat. Despite the setup sounding almost the same, the change in perspective and point of view can really make the difference. So it's possible for 24 hours of Teyvat to be 24 minutes on Earth, but only from the perspective of someone on Teyvat looking at Earth. Again, we have to be careful here. 24 hours of proper time on Earth would be 24 minutes of Teyvat's proper time, but 24 minutes of Teyvat's proper time doesn't translate to a proper time of 24 hours on Earth. Someone on Teyvat would see Earth moving at around 99.986% the speed of light, so Earth's time would appear to be dilated. Likewise, someone on Earth would see Teyvat moving at 99.986% the speed of light, so Teyvat's time would appear to be dilated. For a bit of fun, I'll try and show you how fast this speed is. The average distance between the Sun and the Earth is known as 1 astronomical unit, which is approximately about 150 million kilometers. As we all know, it takes one whole year for the Earth to completely circle around the Sun once. We can calculate the circumference of that circle to find the length of the orbit and divide by 1 year to get the average speed of the Earth around the Sun. We find that the Earth orbits the Sun at approximately a speed of 29,800 meters per second. To put things into perspective, Teyvat is moving more than 100,000 times faster than this. Now if we took Teyvat and let it orbit around the Sun with its speed at the same distance of Earth, it would take only about 52.26 minutes to completely circle around the Sun. Not even an hour. Before I finish things off, I just want to put a little disclaimer. An object that's moving in one reference frame doesn't always mean that the object will appear to move more slowly in time. This has something to do with the Doppler effect, but I don't think I can do its explanation justice. Instead, I would like to recommend this amazing video, Is Time Dilation Just a Clock Issue After All? By the channel Physics, Problems, and Solutions. To recap, I first started by going over the basics of how relative velocities work in Galilean relativity. Next, I explained the two postulates of special relativity by providing an explanation as to why Einstein thought to consider a constant speed of light. Then, I derived the equation for time dilation without gravity, followed by an explanation of proper time and the spacetime interval. After that, I gave an overview of general relativity, and we took a look at the Schwarzschild metric to derive a time dilation equation that accounts for both relative motion and gravity. And lastly, we showed how it's impossible for 24 minutes of proper time on Earth to be 24 hours of proper time on Teyvat, but it's possible for 24 hours to pass on Teyvat, but only 24 minutes elapses on Earth. It's extremely often that when you take the physics of a game seriously and actually try to calculate things, the numbers will almost always make no sense. The 24 minutes for us being 24 hours in Teyvat gave us a nonsense answer, but the reality is that it's just a gameplay thing. There are some games that play out in real time, but I have a feeling that, for Genshin at least, it's probably for the better to not have it that way. Think about this from a game design standpoint. If it actually took 24 hours for a day to pass in Genshin, it might make the world look stagnant, like as if nothing was happening. However, if you have time flow at a faster rate, it can allow for people to see the world in different colors. Literally. If you observe how the lighting changes throughout the day, it's really quite noticeable, and this can help make things look interesting for players in, an open world game that often promotes exploration. Genshin is a beautiful game, and I personally think that having to wait a whole 24 hours before you could see the sunset in Liyue would be rather disheartening. Even if you could always adjust the clock, I don't want to imagine how many times you'd have to go into and out of the menus just to get the lighting correct on the screenshots. Oh wait, we still do that anyway. Whatever. I'm glad that I can look at the scenery of Teyvat and admire its beauty. If you found this video interesting, be sure to hit the like button, comment your thoughts, and share it with others to help promote this video in the YouTube algorithm. As you might know, there's some weird stuff going on in YouTube right now, and a lot of creators are really feeling some weird drops in viewership. I'm not really sure if I'm experiencing it, because, well, I did just come back from a long hiatus, so there's a lot of factors that I can't really say for sure, but whatever the case, any support would be really useful. I cover a lot of physics, math, and even engineering topics on this channel, so if you find that sort of stuff interesting, be sure to subscribe so that you don't miss out. You can also help out the channel by leaving a super thanks or by becoming a channel member. Like I mentioned earlier a few times, I am quite interested in considering analyzing Child's experience in the Abyss. I'm pretty sure that this will probably be one of, if not my most difficult to understand videos, and I apologize for that. If there's anything that confuses you, don't hesitate to ask. I'll be more than happy to answer questions in the comments to the best of my ability. So, yeah. Thanks for watching and hope you've enjoyed.